My name's Don Bropes. I'm the first senior mentor for Washington, D.C., and I'm kind of the coordinator moderator here for today. This is the Artificial Intelligence in Industrial Applications Conference. So is that the one that everybody's supposed to be here? If not, there's time to go and try to find the next one. But with that said, it's my pleasure to introduce Hauck Schmidt from BOSCH. He heads the data mining services at BOSCH, a global strategic initiative reporting to the CEO. He aims to unlock the value of data that things, as in the internet, dang it, I think we just lost it. Bear with me a second here. With that, we may have to freelance here for a second. But anyway, I'd like to start with the presentation, and he can give you a few more details of his background.
Thank you. So yeah, maybe just to complete the introduction briefly, my name is Hauck Schmidt. I work with BOSCH now for roughly 26 years. Have been heading a department in corporate research for a while where we've built up teams that were looking at applying artificial intelligence in industrial applications, and I want to talk about that a little bit today. Maybe before we get started, let me see if this thing works here. It doesn't. Oh, there we go. I really think this is awesome what you guys are doing here, so my big appreciation for everyone here to join this robotics competition, especially for teams that BOSCH is sponsoring. I want to wish them all the best. Good luck for the competition later on, and let's give all of you a big hand for joining today here. All right, so artificial intelligence. When you think about this, there is a lot of things that play into this term, right? So the first question is, what is this even? We already have problems defining what intelligence is when we talk about humans, but now we talk about the artificial intelligence. And I thought maybe illuminating a bit the hopes and the challenges that we have from various perspectives, and especially the perspective of industry, of how they use it, might be an interesting thing to do. And I want to start maybe with a quick look at how society looks at artificial intelligence. And the best way to do this is to take a look at film, right? Because film is really the medium where they strip away all the technical hurdles that you guys have to face in doing the competitions. Everything just works smoothly, and they can focus on really what we expect and what we fear perhaps from this. So I think fear is already a good segue here. This is sort of one way of looking at the future of artificial intelligence. It's this very doomsday view that the machines will overtake us all and will be dominating mankind. There's the robot Maria from Metropolis, back from the early parts of the last century. We have Dave here we have HAL 9000, who is talking to Dave here from the science fiction film 2001. In this case, he is just casually opening up to Dave that he will not let him back into the spaceship anymore, and he will have to die in space. So sorry, but he can't do that. Open the door. Then we have the Terminator movies, of course, right? But there's any number of those. That's one way of looking at it. And of course, there's the more positive view of artificial intelligence being helpful for us, being something that we can use every day. Everyone knows Data from Star Trek. In the 50s, there was Robbie the robot, bottom left there, who was trying to help out as best he can. R2-D2, and then Surge from the Caprica movies, a TV show actually a while back. Helpful agents, I would say, that operate in some environment with humans and try to make themselves useful. So I call this the Utopian View. Now, the question, of course, is how does that help us? How does this view help us to look at what we expect from artificial intelligence? Being an industry, we have a very utilitarian view, right? So we want to get things done. We want to have some improvement in a product that would help us solve problems. So with that in mind, does this really help, right? So I think what these views, both the negative and the positive, have in common, they are sort of very embodied. You always have the intelligence somehow in a physical body, a robot or something. And they interact in some environment, right? They interact maybe in a household or in something that would be of practical use. And I think this is maybe a good starting point from an engineering perspective to start breaking down what is sort of at the core of artificial intelligence. And the way to look at it that I found most useful is via looking at it as an intelligent agent. So an agent is someone who works or lives in some environment, something in a very general view here, some context that it's embedded into, and it interacts with that, right? So we have this intelligent agent that perceives something in the environment. It has a view now of what is going on. Now it has to do some planning, some thinking, what it wants to do with this. And it uses some knowledge base in order to do that. It plans some action and then performs that action in an environment. So very general top-level view. One example could be maybe a chess game. So this has been around for quite a while. Chess computers are well known. The environment is very simple. There are very few rules that have to be followed, very few possible moves that can be done. And there is a goal behind it, of course, to win the game. And then the agent, of course, is the one that would play this game, maybe against a human. Doesn't have to be mechanically enabled there as this one is, but everyone knows chess computers. And that used to be the benchmark where people said, if we ever achieve this, then we have artificial intelligent agents going. So that was done, I don't know, sometime back in the 70s or 80s. The chess computers came out. A little later, they started beating the world masters of chess. And then people said, yeah, but that's rather trivial. They just do a big search, right? And so this is not really intelligence. So then the definition was moved up. And this is sort of a phenomenon we see. Every time we solve a problem, it's no longer artificial intelligence, right? So the artificial intelligence is always one step further away from what we can achieve at this point. My point here is, I think it is. I think we are on a gradual scale from very dumb systems to very smart systems. Chess was one step on the way. There are some others. I'll go a little bit into that a little later as well. It's also useful, perhaps, to distinguish between different types of environments. Of course, there is the physical environment, and this is what you guys are mostly dealing with in your competition. You have some arena or something that your robot works in. There are some rules that are set, what the robot is allowed to do. You can perceive this environment with any number of sensors, depending, again, on the rules. If we do industrial applications, it's more determined by costs than by rules, but we can choose to take any of these sensors. The very simple one would just measure contact if you run into something. Perhaps there's a force sensor behind it, so you know how much speed you had when you ran into it. You can have inertial sensors, vision sensors, depth sensors, anything, acoustic sensors, anything you could imagine sensing that might be useful for solving a task that you have. And then on the output side, in the physical environment, it's mostly about motion. It's maybe sometimes grasping stuff or probing or so on. So this is the space in which the physical environment, robotics, works. You can imagine as well just a virtual environment. So you might have an intelligent agent that doesn't have any connections to the physical world, just works in the virtual world. We call those web services or bots or so on, right? So those are also well known. Here the roles are a bit reversed. Typically the agent initiates the whole interaction with a query or command, right? There's a command going out saying, I don't know, what are the gas stations, where are the gas stations in this area or something. So it needs to look up a web service that finds the gas stations. That web service responds with a list of stations that it finds, and then the agent can go on doing what it was doing. And there's a third category I think that's useful to break out as a separate type of environment, that's where these agents interact typically with humans directly, right? So the user interaction that you see. And here you have typically the human initiating the conversation. Sometimes it's not, sometimes the agent is doing this. But the way that humans would communicate with the machine here would be typically via buttons, keyboards, mice pointing devices, and more advanced maybe gestures or voice, right? So these are things that are now almost solved, I would say. On the output side, you have the very old systems that had just text output. More nicer output would be in graphics, 3D graphics perhaps, haptics, where you get some haptic feedback on what was going on, or even voice output, so the system can talk to you, you can have a conversation with it. But there's not really anything this agent can do to change the world around you, right? So we maybe consider this a bit of a safe agent because all you can do is talk to it. Well, maybe not, right? In the background, it could clear your bank account or something with these services, so you have to watch out there as well. So just to give an example of how this would work, we're back to this picture of an agent here with the 3 blocks: perception, planning, and action. And we want to do device operation, right? So imagine you're in a car, you have your radio, your MP3 player there, perhaps a web browser or something, but you want to drive, you don't want to be distracted doing this. So how would you operate these devices safely in a car? One element is, of course, again, the human interaction of it. So what you see today in cars is actually speech control and gesture control. So there's a unit that can recognize your speech, recognize gestures. At that point, you have the written text, basically, of what you were saying. And sometimes that's enough. If you just give commands, right, radio on, you just have to look at the words, you can map them into actions, that's enough. But if you want to have a bit of a more intelligent discussion or interaction with the system, you would allow you to give natural language input. And then having the written sentence sitting there doesn't help you much because it's a very complicated structure and you don't really know what the user wanted. So what we need is something that understands what you were saying and translates this text into some semantic representation that the system can deal with. And it's not just voice, it's also gesture. So as an example, if I sit in the car and I paint on the map an area and say, what are the prices of the cheapest gas stations here? Let's take that example again. The system has to put those two things together, right? It has to recognize, okay, there was a gesture on the map that indicated an area, and the user was saying something, so probably related to what it was gesturing there. And now let's put this together, and only together this makes sense because just the text doesn't tell you where to look, and just the gesture doesn't know what to do with this areas. But together it's clear, look for gas stations in this area that was indicated. Search by price, right? And then give an output and saying the cheapest one is there, right? So suppose that works in the background. Now the planning part is about how to put all these responses together. You have, 10 different web service calls on the back end. You have all these responses from each single one. You have to put it back together and give some meaningful response to me, the user who asked this question, right? This is what this planning, the response generation does, creates a human understandable result, either as voice or text or some graphic map display or something. And the action in this case would then be to actually output it on those devices. Now, the second part is this virtual environment. And with this example, I want to show that this classification I did before into different environments can be overlapped. Like in this case, we have 2 environments that are actually being used here. So this perception that I mentioned before now goes into a planning task in the virtual environment. And there we do this decomposition, right? So gas stations, cheapest gas station in this area. So first of all, geocoding, what area are we looking at? What type of point of interest gas stations? Okay, so I can look up in my set of web services, there's one on gas stations, gas buddy perhaps. And I send out those commands and queries to each of those web services. They respond with the status updates. That's my perception cycle, and then it goes back into the planning and action. So what you see is a bit of a fractal thing going on here, right? So you have this top-level view, perception, planning, action, and now we just inserted another cycle of that inside. for some more intelligence, right? And this allows us to become a little bit more intelligent in the response to the humans. So enough theory. Let's have a look at what this actually means. How did we use this at BOSCH? We've been working since 2000 on a project on natural language understanding. This is now in products. This took a while to do, but back then there was a big sort of gap in how to do this with the available hardware, right? So I promised to talk also a bit about the challenges in applying AI. And one of those challenges is definitely the hardware available, the performance, especially if you're talking about an embedded system, something that sits without a big server infrastructure, maybe in the dashboard of your car, or even inside your washing machine, right? You don't want a supercomputer in there. That would just make it too expensive. So we have to make do with what's available there. Today we are looking at three main areas where we want to apply natural language dialogue assistance technology. I already gave you an example of mobile assistance, so how language works in the context of a car. Challenges there are how do you avoid distracting the driver from operating the system while they're supposed to be driving, right? So keep your hands on the wheel, keep your eyes on the road, and just have the interaction as a secondary task. We think natural language can help with this. But we're also looking at home assistance, of course, right? So imagine a world where your fridge knows what's inside of it, and you can ask your home what you can do with the stuff in there, right? What can you cook? Or you would tell the system to start the oven a bit later than you had originally scheduled, or turn the light on in some room. And then there's the whole professional space. So when you have professionals go out and repair things, or even if you yourself want to build something and do it yourself operation, you could imagine an assistant helping you with that. So you just finished screwing in the boards, and now you would ask it, what's the next step? What should I do next? And the system knows about what your goal is, what your steps were, where you are on that, and so on. So this was one big topic. Service robotics may be a little bit more close to what you're doing here. We have an extensive research project also on service robotics. And before I go into some of the more, let's say, advanced things we were doing there, I'd like to play a little video on the BOSCH lawnmower that you see up on the top right-hand corner. Maybe if we can have the first video. That's myself, maybe the video. There we go. So I asked them to mute the audio here because it's truly just music. But what you see here is a lawnmower that mows the lawn autonomously. That's not really anything big and new. There are a couple of those on the market. The interesting thing about this lawnmower is that it can orient itself in your garden, right? So what you have to do is put a wire on the circumference of your garden. And that's about it. And the robot then just starts mowing. And when it hits the wire, it has some logic inside, some intelligence that tells it where on the periphery it is and what next route to take. So it always knows where it is. And with that, it can do a very detailed and systematic planning of how it will mow your lawn versus just randomly doing it like the vacuums do today that we know as well. And the second element is, of course, once it runs out of battery, you expect it to go back to the charging station. And for that also, it has to know where it is and where the charging station is and maybe the shortest way to get there. So it does that as well. And there you go. It docks back into the charger by itself, charges up. So there's very simple artificial intelligence at work there, nothing really too complicated. But again, the challenge is to put all this onto a small 8-bit microcontroller on this lawnmower, right? There's no server attached, there's nothing, no intelligence in the cloud or anything, so this was a bit of a challenge to make it all fit in there. A bit more on the advanced side, you see the PR2 robot, many of you may know this one. This was a program initiated by a company called Willow Garage, end of the last decade. They saw this issue that whenever a researcher or someone who has maybe some experience in vision and computer vision, and they want to do some tasks in robots and robotics, The typical way to do this back then was you had to start building up your own robotic platform, and you spent 2 years perhaps building that up, and then you had a robot running around, and then you could start taking images and doing your PhD work on vision that you actually wanted to do. So what a waste, they said. Why don't we standardize this? Why don't we create a standard robotic operating system called ROS, and also create a standard hardware? And they did that, and they had a competition for 11 of these robots that they built, had universities and then companies participate, and with ideas of how to use this. So we participated in that. We won one of these robots for 2 years in a project, did some research projects with that. We're also very actively posting software modules on ros.org, right? So giving back here to the community as well to enable others to start robotic work a little easier. What did we achieve? What was the result there? I think one of the interesting concepts that came out of this work, at least for me, was the notion that maybe we're chasing the wrong goals by having something completely automated. If you think of automation as more of a continuous thing, right? So there's completely manual work, let's say a completely remote controlled robot. And on the other end of the spectrum, you have the fully autonomous robot that doesn't need any interaction or any help from humans. There are various steps in between where you could imagine maybe we can just share this autonomy, right? So there are things the robot does very well, and there are things humans do better. And as long as it's not too much and it's just occasionally that you have to help, maybe the best way to make progress here is to have humans help robots. And this is what we called shared autonomy. And this is an example of where the human understanding of the context helps the shared autonomy. And there's another short movie on this, maybe with audio this time. So that was the PR2, Adam Allen. Okay, so this, at least to me, wasn't clear at the beginning. If you have a cereal box and you tell it to grasp, that there are some issues. If you grasp it at the top, you can't pour it, right? And so this context of what you want to do with it flows into how you want to grasp it, actually. And this was what we wanted to solve here by having the human help. So what are challenges in service robotics today? We have solved the problem of standardization. I think ROS is a really good solution to get progress in research, at least on this front. What is remaining is cost and also things like dexterity, right? You saw this robot, it had sort of claws there. This wasn't really very sophisticated. You want to be able to do much more fine granular things with your fingers and hands, so more sophistication in the arm and in the actuation. And that drives up cost. This robot originally cost $400,000, and I think 150 went into each of the two arms. So those arms are really expensive. If we want to move towards some products that we can use at home, some service robot at home, this has to become a lot cheaper. And that's a challenge. How do you make it cheaper, smaller? What sensors do you really need versus which ones would just be nice to have? Those are things we're trying to figure out here by just sort of going from the gold version here of a PR2 with many, many cameras and different sensors to decide what we actually need in order to make this more useful. Good, so we started the research group on robots, and then we figured, well, that's not very far away from a car, an autonomous car, right? So you have perception, you have actuation, it moves. In the future, cars are electric, so that's also the same thing, right? So why not just look at the car as a robot? And so we started working on automated driving, we call it now. We participated in 2007, I believe, in the Urban Challenge, in the DARPA Urban Challenge, together with a team in Stanford. Came in second there. I think we lost to CMU. But the experience was that that was sort of a setting where cars drove in a controlled environment, but with almost real traffic interaction. That was a pretty good progress back then for automated driving. Since then, of course, you've heard the news that every major car company, along with Google and some others, also BOSCH, have cars on the roads. We have a car in California, in Palo Alto, driving on Highway 280 up and down there, as well as in Stuttgart, Germany, and a lot of international team working on progressing automated driving. What we learned is it's actually very different from robotics. You have to make real-time decisions. You don't have time to think about where your hand moves for a minute or so. Traffic just happens, so you have to react to it immediately. I would say most of that is solved. There are some, of course, some problems or some challenges, I would say, still in very complex situations, especially in the city. That's why we are focusing mostly on highway driving, because, again, the environment is rather controlled there. You don't have typically pedestrians running around. The other challenge is that you've all seen these cars. They have this big Velodyne laser scanner on their roof. Not a very pretty sight if you look at car design. Also very expensive. So the challenge here is, again, to make the sensors cheaper, bring them down. The reason it's up on the roof is because from there you have a very good vantage point onto your environment, and you have a view all around your car. If you pull it down into the passenger compartment, the view is lower, and you don't see the environment as well. So there are challenges in solving this. I think everyone is working on those. This will be solved at some point, and you'll see gradually autonomous functions moving into cars in the next couple of years. I would say in 2-3 years, the first functions should come into products there. So rather than show you how our car drives, it's more or less the same like all the other cars drive. I wanted to focus today on some sort of more advanced questions behind that. So once you have a car that drives autonomously, how would this work? And how would you hand over the control when you drive to the car? How would you pull it back in a way that there won't be any dangerous situations arising from that, right? What are other areas where artificial intelligence can help you plan your trip or schedule your trip? And so there's a short video on some concept ideas that we have here. Please roll the video.
Welcome to our vision for a highly automated car and its unique driving experience. Although it looks like your common everyday car, a host of smart new features ensures that driving is no longer a chore. It helps to reduce the load on the driver by taking care of highway driving. Philip, a young professional, has been using his new car for a few weeks now. The car has been learning from his routines and can predict destinations. On selecting the destination, the car allows Philip to optimize his time by balancing the share between manual and automated driving. As Philip sets off, he looks at the upper left corner of the instrument cluster, where the drive state indicator is located. It is a quick reference for the time left in the current driving mode. Apart from the regular navigation view, the split display provides Philip with an overview of his route. With this, Philip has a clear picture of where automation is available. He can access additional features with aid of the menu on the left. As he approaches the ramp to the highway, one of the maps switches to the top view so that he has a better view of his surroundings. After entering the highway, the drive state indicator communicates to Philip that automation is available. Also, two special buttons on the steering wheel start glowing. As Philip presses them simultaneously for 3 seconds, the car switches to automated mode. Philip can now confidently take his hands off the wheel as he knows that the car is in full control. With the free time in hand, Philip decides to get some work done and opens his office inbox via apps. For a better view, he moves the inbox to the top panel and goes through his unread messages. Philip can perform common actions by interacting with the on-screen buttons or with voice commands. He starts to dictate his reply to an email. It's not the same as working at his desk, but with the new car, Philip can be productive even while on the road. While on the highway, the car encounters a slower-moving vehicle in front and sees an opportunity to change lanes. It communicates its intention by displaying a visual on the instrument cluster and a notification on the central display. If Philip wishes, he can select this notification to access the top view and monitor the maneuver. Once the car has completed the maneuver, Philip can rate it based on common driving parameters. This helps the car to learn his preferences and to improve its motion behavior for better comfort. Having taken care of all the important work, Philip still has some time left before taking back manual control. He decides to relax and watch a few online videos. When it is time for Philip to take back control, he is notified in steps. With a few minutes left, the drive state indicator switches to orange, and then red, depending on the urgency of the situation. If Philip still doesn't take back control at this point, the car would find the next safe spot on the shoulder and pull over. Switching to manual mode happens in the same way as activating automation. As Philip presses the buttons simultaneously for 3 seconds, the car switches back to manual mode. On reaching his destination, the car provides Philip with some smart statistics on his journey. At a glance, Philip can compare the efficiency of the car in manual and automated modes, and also his savings. From being a mere mode of transport, the car has evolved to become a part of Philip's digital lifestyle. It allows him to be productive when he is on the move and can be relied upon for needs far beyond mobility.
Good, so everything's solved, right? There are some things behind the scenes that still pose challenges, of course, not least of them also being, how do you actually prove that an autonomous car is safe on the road, right? What is your justification for allowing it into traffic? Bosch being a big provider for the automotive industry, we have a lot of experiences in bringing components into the car And whenever there is a safety critical aspect to the component, there is a huge amount of testing happening. For example, any braking system that is new gets tested for enormous amounts of miles before we know that it's safe, and also our customer, the car manufacturer, believes it's safe, right? Now, for a small component, you can do this. You can test it in all sorts of situations, but an entire system like a car is so complex, you can no longer just write down all the different situations it could be in, right? It's just too many. And so this is a bit of a challenge still to come up with a concept that allows testing this car without making it, again, too expensive. The criteria that you typically use is to say, well, it should be safer than when a human drives, right? So fewer accidents, maybe fewer fatal accidents than a human. And then you look at the statistics, and a human has maybe one fatal accident on average every 10 to the 9, I believe it's hours, or perhaps it was kilometers, but at that size, it doesn't really matter. If you want to drive 10 to the 9 kilometers, that's not doable, right? This is billion kilometers, it's very, very far to drive. So we have to find some other ways for validating this, and this is still a challenge that we have to see how to address it. Other than that, of course, again, I mentioned that already, making sensors smaller so that you can also design them in a certain way, and cheaper, of course. Good, so final practical example today focuses on this new thing that everyone talks about, Internet of Things, right? So we all know the past 15 years or so was the Internet of People, social media, connecting people to each other. And what is happening now is that all the things that you put out, that you buy, washing machines, sensors, everything basically will be internet connected. And there's an estimate, I think, from Cisco that by 2020 there will be 50 billion things that are connected in the world, right? What does that mean, right? So now we have this huge set of things that pipe data to some cloud, and then this is sort of supposed to be on the right-hand side, the cloud that all this data goes into. And there's a huge opportunity in this, right? So Bosch is looking at 5 domains in this Internet of Things: healthcare, building technology, mobility, energy, and industry, so connected industry. And in each of these, there will be many sensors that are deployed that are directly connected to the cloud. And you have the opportunity, of course, to optimize using this information. The idea is the same as with social media. You have maybe 1 million deployments, right? 1 million Facebook pages. Everyone puts their stuff in. Information goes back to some company that evaluates the data and then tries to improve the service in some form. Sometimes it's for placing the right advertisements on the page, but sometimes it's also just to make the page much more easy to navigate for everyone. And it's the same thing here with sensors, right? So you have all these sensors reporting information, and we can use data analytics or data mining to see if the deployments allow us to optimize something in maybe terms of energy efficiency or productivity, or any other thing, use of resources, using fewer materials to produce something, assessing the risk more accurately, or just even making sure the maintenance of our machines is scheduled correctly, right? So these are areas where the Internet of Things promises a big commercial impact, and of course there's huge interest from all sorts of companies to go into this space, and Bosch is active there as well. One topic I'm currently working on with my current team is in all those areas, but I picked out an example here from this topic, connected industry. So you have manufacturing lines where parts are being produced, and those parts generate data not only when they're deployed, when they're sold, because they're internet connected, they already generate data during manufacturing. But so while they move through the production line, a lot of data is generated. Anything about what the force was when a certain screw was tightened, or what the oven temperature was when it was sintered, or anything like that, it gets tested along the way a few times. So all those test results are available. Some of them occasionally fail in the field, right? It's very few per million, but that happens. So you can pull that data back into the system and look at what was different on these, right? Why did they fail? Is there anything different in the test or process parameters on this specific part that it failed as opposed to the others where it didn't fail? And also logistics data, so moving things from A to B, moving things into the production line and away from it. Can that be done more efficiently? So those are things we analyze with the goal of, again, reducing maybe the test time of a part or calibration time of a part. Scrap cost, this is especially when you build safety relevant products. You don't want to deliver anything out into the market that could fail in the market, so you rather err on the side of caution and you scrap a lot, right? So there's a lot of stuff that's thrown away because we're not that certain that it might not fail in the field. But again, is there some way of optimizing that and not throw away so much? And all the way down to predictive maintenance and yield improvement. So that's the overview of current topics we're working on at BOSCH. And so to come back to the beginning where we talked about this grander view of artificial intelligence, I thought it might be interesting to close maybe with 3 slides about where this is heading, right? So the first one is looking backward into the past. When did AI start? If you look into the history, AI started way back in the ancient times of Rome and even before that. But for our purposes, let's have a look at the time period from the birth of modern computers, because we typically think of AI as something that runs on a computer, right? All the way to today. The term AI, artificial intelligence, was coined back in 1956 at a conference in Dartmouth from some researchers. And following that, there was what they called the golden years of artificial intelligence. A lot of research money went into it. Some very good early results fueled this whole field. Everyone was really excited about it. And of course, up to the point where the disappointment set in and people noticed, okay, so we have some way of solving what we think are problems that make machines intelligent if they solve them, but those are only really toy problems, right? Very simple things. Anytime we try to make it more complicated, it fails. There were, of course, very limited computing power available at the time. There was not much opportunity to bring all the context knowledge into the access to the machine. So funding dried out. That was until the early 80s when then someone discovered, hey, we can actually overcome some of these problems, and a new boom set in. This time around expert systems trying to code knowledge by rules, right? So a lot of if-then rules. This was called knowledge engineering, so there were people that wrote all those rules, and there were applications where it worked really well, so the funding went in again, and there was a big boom again. At the same time, mathematicians and researchers were looking at what is called connectionism. So the idea of not using maybe a rule system, but maybe something more like a neural network where you feed in information, something happens in between that no one really knows, and out comes something useful. And they discovered a way to train neural networks called backpropagation during this period there. But again, there was a disappointment set in. They noticed that expert systems are very brittle because it only really applies to exactly the rule set that you put in. If your problem is a little bit outside that parameter space, you get very weird responses sometimes. So it's not that there's any graceful degradation to the system. Very hard to maintain when your environment changes. How do you update the rules? They have to be all updated by hand again. And so this second AI winter, it was called, until the early 90s set in. That's around the time I did my PhD back then. And then since then, artificial intelligence has found its way back, and it's sort of done this a bit in the background. There wasn't really this really huge hype anymore around it. But today you have a lot of artificial intelligence deployed, and it's just not called that anymore, right? A while back, you had Watson, right, beat humans in Jeopardy. You have Siri in your pocket right now, probably same with services from Google or Microsoft. So you have voice recognition there now. You can ask it things, and it understands that. And so we just take that now for granted. But from a sort of longer perspective, this is quite a bit of progress in artificial intelligence. So where are we headed from today? I think today there is a big buzz about deep learning. So again, the neural network type approach, not new. So these things all were known back in the early 90s already, but no one really dared to go into such many layers of a neural network because of the computing power needed. And today we can do this. Many of you maybe have heard of these results. They trained a system on video games, so arcade games, right? They let it look at the screen, and they gave it control over the joystick and button. And everything else the system had to figure out itself. They didn't tell it any rules. They just let it play, and they gave it an evaluation whether it won or not. And so with that, they trained the system, and they actually beat humans with this. So there is now already an example with I talked about environments at the beginning. This is a video game environment of, I don't know, Pac-Man or something of that complexity, so very simple. But hey, anyway, there are computers that play, I don't know, 400 times better than humans now, right, in many of these games, using deep learning. So there is, again, a big hope that this is a way of advancing artificial intelligence on the algorithmic side. So what about hardware, right? If we just look at the prerequisites to have something artificially intelligent, maybe on par with humans, this is a graph out of Ray Kurzweil's book from 2005 on the singularities near, I think it was called. And he projected the available computing power that you get for $1,000 over time, right? Back from 1900 all the way to 2100. And you see this is filled up to roughly 2000 or so where he had data points. But the trend is pretty clear, and I think it's still intact, right? So I just put in a marker there, 2015, where we are today. And you can see there that we are currently somewhere between a mouse brain and a human brain in terms of what computers are able to process, right? And we will very soon be at the level where computers have the capacity to process as much as a human brain does. That doesn't mean we have artificial intelligence on a human level then, because you still need the algorithms to do something smart with this processing capacity, but at least the prerequisites will be there. And then not too far out beyond that, you will be able to simulate all human brains in a single computer for $1,000, right? So this is not that far out anymore, just because of Moore's law and this exponential growth. This chart is very similar. It looks at the available capacity in supercomputers, the highest performant computers at any point in time, and it again goes up to 2005 here. And you see 2015 is already well within the area of where a supercomputer should be able to do something human-like in artificial intelligence, right? I haven't seen any updates on this. You can speculate now whether there are some agencies or companies that may have enough computing power to try this actually. But this is something really exciting. So I want to close with this message. I mean, to you guys, you are living in a very exciting time. You have a career ahead of you. You're interested in robotics and in artificial intelligence, hopefully, and you will witness the first computer that will challenge humans on their intelligence. So this will be an exciting time to see what are we going to do with this capacity. With that, thank you very much, and I want to open it up to questions.
I think we have time for a few questions. If you'd like to ask some right now, raise your hand, speak up.
Yes, please. So are there any companies that make a lot of profit with artificial intelligence, right? I would say, let's say on the side of internet companies, definitely. I mean, Google is building their entire business model based on the intelligence of their search algorithm, and they make huge amounts of money, right? In terms of robotics, there are military applications and some niche private applications that make money, but I wouldn't call this really mainstream yet, right? So what I call service robotics here, the robot in the vicinity of humans that is something that hasn't really happened yet. So this is perhaps about to happen in the next 5, 10 years, but this is really where we're heading with all this. Yeah. Parking cars autonomously, yes. I saw some demonstrations of car companies showing an autonomous parking. Typically, that's an easier problem because you have a very controlled environment, right? You can block the parking garage from any pedestrians, for example, and you hand off your car to a robotic valet or something. When you enter it, the car goes and parks itself. It knows where the parking spots are. It knows that no one will be jumping in front of it. There are no kids playing in there. So it's very controlled, and there are solutions that work, but not commercialized yet as far as I know. The deep learning, what is the idea behind the deep learning algorithm? So the algorithm works as a neural network, and you have a couple of layers. I think there were 5 layers here, where you look at certain parts of the screen, and the computer is supposed, or the network is supposed to learn what that means and how to set the weights on each of these layers, the hidden layers, so that in the end you make the right choice with the joystick to reach your goal, which is to survive or to gather points or something, right? And it has this knowledge about how successful it is doing it, and in between how the weights are being set, there is no, so this is one of the shortcomings of neural networks. You have a very hard time interpreting what those weights mean, right? But there are, of course, mathematical algorithms that tell you exactly how you have to update weights in order to reach your goal. Backpropagation, I mentioned here, is one of them. The deep learning, I think, uses reinforcement learning here to do this. So there are ways that you know how to update them. That, yep. So what will happen if another participant in traffic hits your autonomous car? Is that the question? Yeah. I don't know. So supposedly the car will notice, right? I mean, there are many sensors that tell it, oh, something was hit. And it will probably try to, maybe, the question, what strategy do we give it? The best strategy I would see is to pull over quickly and stop the car and see what damage was done. But you're completely right. There are many such questions that have to be figured out before we can have autonomous driving on public roads. The nice thing is that the discussion around them has started, right? So society has started to discuss now, do we want autonomous cars on the road, and under what conditions do we want them? And that's the important part. In the end, society just needs to agree on, yes, this is what we want. The promise is it would make traffic safer, right? Let's hope that's the case. And if so, then it's definitely worth putting as many cars on the road as you can autonomously. Imagine a future when this is proven, and you have to pay more insurance if you want to drive yourself because it's more dangerous. So you can save money with insurance if you drive it autonomously, and you just take yourself out of the equation there, right?
I think we have time for about 2 more questions. I had one more up on the top floor, and then we'll back down here.
So you touched briefly on how our society views artificial intelligence, but are you worried about how it will be accepted, even just in cars, right? Or planes, where we have computers that are controlling things that can really kill them easily, just with a mistake.
Yeah.
Zeros in the wrong place.
Am I worried about this? Yes, I am. No, I think this is not something for me to decide. This is something that we as a society have to discuss to see, do we want to take that risk? Just to be fair, humans also kill children in traffic, right? And they also down planes. I mean, we just had the plane in the Swiss Alps that came down because of an intentional human error, right? So those things happen, and you have to weigh the pros and the cons. Where is the chance bigger of saving lives? And I think in the end, it will be a discussion of exactly that. If we can show it's safer, I'm pretty sure society will decide that we want autonomous agents driving our cars and planes. Yeah. Yeah. Yes, I do see that transitional. This was an example how we can move into these kind of problem domains with some practical use, right? Without having to have it solved completely first, because you can try to solve it perfectly and that takes you 15 years, or you can almost solve it perfectly and go out in 3 years on the market and then work on the rest as you go. But yes, I mean, at some point, this will not be necessary, sure. Yeah.
One more question.
With your AI systems or any AI systems in the industry, do you think it is valuable to have a system that says, let the human take over because the robot is malfunctioning or not working correctly?
So is it necessary to have a mechanism to let the human take over if something goes wrong? Sometimes. So in a car, definitely yes, right? So you have this high-speed thing going on. There are decisions to be made, and if the car just turns off or the agent turns off, the driver has to be able to take back. Or even if not, right? Just because he thinks he wants to do it himself, he has to be able to be in control. If you have a robot that transports things from A to B, at 1 mile per hour somewhere, and it breaks down, you could imagine that a human takes over, but you can also just stop it there until someone comes and fixes it, right? It doesn't pose any danger. And I think the question is really, does it pose a danger that makes it necessary for humans to take over immediately? At the end, anything that breaks down will be tended to by some human, and it will be either moved away or repaired, and then it continues doing what it does, right? And many of those autonomous systems will fall into that same category, I think.
Thank you very much.
Thank you. Thanks, everyone.